Hello, everyone. This is Ashraf Mahgoub. I will be presenting SOPHIA, online reconfiguration of clustered NoSQL databases for time-varying workloads. This work is a collaboration between Purdue University, Johns Hopkins University, Adobe Research, and Argonne National Laboratory, and the work is supported by NIH. So the first thing we are going to do is to introduce what are the challenges in online tuning for NoSQL databases. And the first challenge is that these databases have numerous configuration parameters that control and impact the performance. And in many real-world scenarios, the workload characteristics is always changing over time. And therefore, reconfiguration is needed because the optimal parameters also change. Furthermore, reconfiguration has a cost. For example, if to apply the new configuration, we need the server restart, then during the restart, there will be data unavailability as well as degradation in throughput. And if the workload change is transient, then the cost of reconfiguration might not be recouped over time. And in this slide, I'm showing a very simple example to illustrate the idea of the paper. So in this figure, we see a cluster of Cassandra nodes running with conf1, which is optimized for the current workload characteristics and achieves 70K ops per second. But over time, the workload changes to a different workload. And now our configuration that is denoted as conf1 is becoming suboptimal and is only achieving 40K ops per second. And then if we reconfigured our cluster to conf2, then our throughput is back up to 60K ops per second because we picked a configuration that is optimized for this workload. But then over time, the workload gets back to the old characteristics, workload 1, and then conf2 becomes suboptimal and achieves only 30K ops per second. The problem here is it is not always desirable to switch between configurations because changing the configurations has its own cost. And if the changes in the workload is not long enough to recoup that cost, then the overall reconfiguration process will be harmful to performance over time. And to understand better what this means, we show this very simple example where we reconfigure 2 Cassandra servers in runtime. The x-axis shows time in seconds. The primary y-axis shows the throughput in terms of ops per second. And the secondary y-axis shows the gain. And gain is defined as the extra number of operations that we were able to perform because of the reconfiguration. And we can see that at this point of time, we were achieving only 40K ops per second, but we have this other configuration that can achieve 50K ops per second. So we go ahead and reconfigure the servers. The first thing that we notice is there is a transient degradation in performance, which causes the gain, the dashed line, to go below 0. So it's a negative gain for now. And then after some time, the system reaches the steady state, achieving 50K ops per second that we were hoping for. But unless the workload lasts for this X marked point, the gain will be a negative gain, which means we need the new workload to last beyond this X point before we start seeing a positive gain of the reconfiguration. So this is the limitation of all prior works which implement the configuration tuners. The first thing they do is to monitor the application in runtime, and whenever the workload changes from the application perspective, new configurations is pushed to the database management system cluster. And this does not work for dynamic workloads that changes very frequently because the lack of cost-benefit analysis as well as causing performance degradation compared to static or default configurations and also making data transiently unavailable to users. And this is where our solution comes to play. We introduce SOPHIA that adds a workload predictor, a cost-benefit analysis model, as well as a controller that finds a reconfiguration plan. And this is how we represent a reconfiguration plan. It simply says that at which points of time we apply which configurations. So at time t1, we apply variables v1, v1, 2, etc. up till time tn, where is the end of the workload look-ahead period, we apply vn1, vn2, etc. And we use our distributed protocol to gracefully switch between the older configurations and the new ones without degrading data consistency and availability requirements. So the first thing we do is to use Rafiki, which is a static tuner that identifies the most impactful parameters and for a given phase of the workload, it finds the optimal configurations. And based on the impactful parameters that was identified by Rafiki, we found that most of them require a server restart for the new values to take effect. And for predicting the workload, we implemented a very simple in-order Markovian model that represents the different states of the workload and predicts what would be the future patterns of the workload. So this is how SOPHIA estimates the cost of reconfiguration. And this cost is because when we apply reconfiguration, there is a downtime for each server. And if we didn't apply the configuration, there would have been some operations that we would perform. So basically, this loss function estimates what would have been the number of operations that we had achieved if we didn't perform the reconfiguration. And it takes into account what is the workload looks like at time tk, what is the set of configurations that we use at this time, and how long does it take for a single server to restart and resync with the rest of the cluster. And when we estimate the benefit, it is simply the difference between the cluster's performance with the new configurations versus with the old configurations. And with the loss and the benefit functions, we apply genetic algorithms that search the vast configuration space and finds the best plan that optimizes the performance over time. Then we apply our distributed online protocol that gracefully switches between the old configuration and the new configuration without degrading data availability. And the first thing we do is to identify what we call the minimum availability subset, which is defined as the subset of servers that cover all data records exactly CL times. And we show a very simple example of 4 Cassandra servers with a replication factor of 2. So each data token is replicated twice. And according to this particular data placement, the minimum availability subset could be servers 1 and 3 or servers 2 and 4, which means we can reconfigure servers 1 and 3 concurrently while servers 2 and 4 are up, and vice versa without losing data availability requirements. Afterwards, we apply these 5 steps. We first drain, which means we flush all uncommitted data records to the disk, which is needed to avoid long and expensive data repair processes. We shut down the running Cassandra process, swap the configuration file, and restart the new Cassandra process, wait for some time for the new server to sync with the rest of the cluster. And here we show the 3 use cases that we used for our evaluation. The first use case, which is called MG-RAST. MG-RAST is a real workload trace from the largest metagenomics analysis portal. The workload in this trace has no daily or weekly pattern, as the requests and the jobs are being submitted from all across the globe. We noticed that the workload changes very drastically over a few minutes, and it is only accurately predictable for a look ahead of 5 minutes. The second use case represents a bus tracking mobile application, which shows a strong daily and weekly pattern, and the workload is more predictable for longer look ahead periods, such as for like 1 hour or 2 hours. The third use case is a simulated workload trace from batch data analytics jobs that is submitted to a shared high-performance computing queue. And using user and job profiling techniques, job execution times can be predicted with high accuracy and for longer look-ahead periods. And this figure shows the performance of using SOPHIA on top of Cassandra compared to 3 baselines. The first baseline is simply the default, which is the Cassandra's out-of-the-box configurations. The second one is the single static configuration that is optimized for the workload, given that we have perfect knowledge about how the workload would be from end to end, which is not a realistic baseline, but it serves as the upper bound for any static configuration technique. The third technique is we call the naive approach, which always applies the optimal configuration for the current phase of the workload. So every time the workload changes, it will reconfigure the cluster to the optimal configurations. And the applications are ordered in the more predictable So the rightmost application is the most predictable application. The leftmost, which is MG-RAST, is the least predictable application. And we noticed that with longer and more accurate workload predictions, SOPHIA can find better configuration plans that achieves globally optimized performance. And we also noticed that compared to the static Oracle baseline, which is a direct application of all static tuners in prior work, and also assuming that we have perfect knowledge about the workload, SOPHIA achieves better performance for the bus tracking and HPC, while it suffers from a little bit degradation of performance for the MG-RAST due to the very short look-ahead period that we have for this particular use case. And compared to the naive approach, we see that SOPHIA achieves better performance in the range of 25 to 30% across all three use cases. So we also apply SOPHIA to Redis, which is a very popular in-memory data store. Redis used to offer a feature in the versions before version 2.4 that is called virtual memory. And this feature allowed Redis to work with datasets that can spill over from the available memory. But since version 2.4, this feature was removed. It was deprecated as it caused serious performance degradation in many real-world deployments of Redis. However, we used SOPHIA on top of Redis in version 2.4 to automatically tune when and when not to enable the virtual memory, and also what is the maximum size of the virtual memory to use in runtime. And the takeaway is with SOPHIA, it was able to achieve the best of the two worlds. Whether when we enable the VM, we have the ability to serve jobs that is larger than the available memory, but then if the job does not meet, if the job access pattern does not meet our VM size, the throughput of the database becomes very slow because most of the requests are being fulfilled from the disk. So by automatically selecting the right parameters, SOPHIA was able to achieve close to optimal performance in every case that we are showing, with different job sizes, different access patterns, and different request distributions. And the major insights from our work is online tuning of NoSQL databases for dynamic workloads is challenging, and all prior works suffer for dynamic workloads, as a straightforward application of these will actually degrade the performance and data availability. We introduced SOPHIA to address all these shortcomings and combine workload prediction, cost-benefit analysis, and genetic algorithm. We evaluated SOPHIA with real workload traces and two popular NoSQL data stores, Cassandra and Redis. And we showed that SOPHIA achieves globally optimized performance and respects users' data consistency and availability requirements. Thank you.
All right, let's take some questions. Please.
Thank you for the presentation, and I'm Himalayan.
Yeah.
I work for Realtor.com. I have a quick question. So NoSQL databases like Cassandra has like hundreds of tunables, right? Varying from cache sizes, different caches, and consistency policies, and topology, and there are so many. How does SOPHIA figure out which of these parameters matters the most, and how does things work afterwards?
Yeah. So actually, this is what you said is a very challenging problem, and we built on our previous system called Rafiki that appeared in middleware 2017. So Rafiki, which we use here as a static tuner, but Rafiki main claims in that paper is to identify which parameters are the most impactful to the workload, so perform like feature space reduction, and then in runtime, when queried with a particular phase of the workload, it can find very quickly what is the optimal configurations for the parameters that was identified. So what you said is a very challenging problem. However, this problem it was solved in Rafiki as well as other systems which we call the static tuners. So SOPHIA kind of builds on that.
Any more questions? Well, I'll ask one, which is sort of what's the next step for this work?
Well, our ongoing project was looking at the problem of tuning cloud configurations as well. So what we found is now you have a Cassandra cluster that you want to host in the cloud. And this adds more complexity to your problem. So you already had 50 plus configuration parameters for Cassandra, and now you have to pick what is the VM size and the VM type for the cluster. And this brings also new metrics to the problem. So you don't look at the throughput only, you're also looking at the cost of your cloud configurations. So this is one direction that we are looking at for our next paper.
All right. Last call for questions. All right, yes, sir. Introduce yourself.
So can you expand more about the workload prediction and how does the workload prediction accuracy impact the whole parameter tuning?
Yes. So frankly, workload prediction is not a new claim in this paper. So there has been lots of work done in workload prediction in different deployments, not only database. And in our paper, we kind of implemented a very simple Markov chain model, like first order and second order model for every use case that we had. Although that more complex predictors can be used instead of the Markov chain. So yeah, workload prediction is a very challenging problem. It's a parallel problem. From our perspective, what we have found is the more the predictable the workload is, then the longer look ahead you can forecast in the future, and the better plans you can come up with, so that you are certain that your configuration decisions are not like greedy decisions. It will not improve your performance for a short period of time, and then your performance will degrade. You have some sort of confidence that the configuration plan that you have right now would be like globally optimized plan.
Sorry. Do you have any like testing result about how does the workload prediction accuracy affect the general parameter tuning result in your paper?
Yes, they are there in the paper, and we also put it in the poster. I omitted it from the presentation for the sake of time, but yeah, please come to the poster, and we can discuss all the results related to the workload prediction and how it's impacting the performance of SOPHIA.
Okay, thank you.
Last call for questions. All right, well, this concludes our session on big data programming models and frameworks. Let's thank all of our speakers.